On the Plas. I hope I pronounce your name correct. The talk is about predictive learning also enables neural networks to learn complex working memory tasks.
Yeah, thank you very much. So my name is Thijs, and I'm very excited to present our latest work today. And yeah, please let me know if the audio isn't working correctly or something. So I wanted to start by this classic study from Tolman quite a few decades ago now, that I'm sure many of you are very familiar with. And in this study, rats had to solve this maze, and Tolman observed that rats who would obtain a food reward at the end of the maze would learn to solve the maze much better than rats who didn't, which of course was fundamental to the conception of reinforcement learning. But also they observed that if rats only started to obtain a reward after, say, 10 days of training, they would then learn much quicker compared to if they were to receive the rewards from the start. So Tolman hypothesized that some kind of latent learning must have occurred during these first days of training, where no objective was present yet, but still some learning occurred that could later accelerate the learning of this navigation task. And recently, especially using AI models, a key candidate has emerged for this latent learning process, which is predictive learning. So predictive learning being learning to predict upcoming observations. And so essentially in these navigation tasks, what that means is that agents will create an internal model of the environment through predictive learning, and they can then use this to solve this more complex navigation task. However, very recently, this neuroscience study here also observed that predictive learning occurs in a working memory setting, very different from navigation. So in this experiment, mice would hear a sequence of tones, and the researchers found that neurons in primary auditory cortex would then predict upcoming tones of these predictable sequences, even though there was no reward or task specified at all. So essentially what we want to explore in this paper is what the function could be of predictive learning in this working memory setting. And and secondly, we're interested to find out exactly what neural mechanisms enable predictive learning to benefit in other tasks. So in other words, how predictive learning engages with other task learning at the level of individual neurons. So to do this, we consider small recurrent neural networks of 20 neurons, and we train them on two different tasks. The first is a prediction task, where networks have to predict upcoming stimuli, and the second is a matching task. And so on each trial, we present two stimuli, and stimuli are correlated such that on the majority of trials, they will be of the same category. And the prediction task asks networks to predict upcoming observations. So the optimal solution is to use the information to first stimulus to then predict the second stimulus. And secondly, these matching tasks, they ask networks to, at the end of each trial, report whether these two stimuli were a category match or not. And so we train networks in three different ways, either by training them only on the prediction task, only on the matching task, or on both simultaneously by just simply adding the loss functions. And what we find is that networks easily learn to solve this prediction task, both the single task and multitask networks, but only multitask networks could learn this matching task. So in other words, networks needed to engage in predictive learning too in order to solve this matching task. And this effect is called eavesdropping, where the learning process of in this case, the matching task has to eavesdrop on the solution of the predictive learning task in order to catalyze learning. And sorry, and so we have identified a function of predictive learning in this working memory setting, namely it can enable the learning of more difficult working memory tasks. And because we've used such a small network, we can now really investigate each neuron and ask how predictive learning was able to benefit this matching task. So we do this by investigating the activity of each neuron over time, shown here as the average across trials, at different stages through learning. So in this raster plot, each neuron is color-coded by how strongly they encode the first stimulus. And so we see at the start of learning, only during the presentation of the first stimulus, indicated here on the time axis, neurons faintly encode the first stimulus. But as they learn the prediction task, the network creates a memory of the first stimulus. So we see that the present representation of the first stimulus now goes up to the second stimulus. So it has used a memory of the first stimulus to predict the second stimulus. And as then learning goes on and the network eavesdrops on this solution to solve the matching task, we see that what has happened is that this memory of the first stimulus has extended through time, so that now the network has both the first and second stimulus in memory to be able to perform the match computation. And so if we can clearly see this if we now plot the activity again, but colored by how strongly they encode a match or a non-match, then we see that the moment that these networks have created this prolonged memory of the first stimulus, they are now able to also encode whether a trial was a match or a non-match. And so we summarize this by plotting the strength of the memory of the first stimulus across time at different stages through learning. And so in this experiment, as I mentioned earlier, the stimuli were correlated. So the prediction task would use this correlation to be able to predict the second stimulus. And we find that if we repeat the experiment but using uncorrelated stimuli, this doesn't work. So if there's no correlation of predictability between stimuli, then no memory will be induced. So there's no memory of the first stimulus because there's no memory needed to predict the second stimulus. And because there's no memory, eavesdropping doesn't occur, and these networks are not able to learn the matching task at all. So in other words, this stimulus correlation of predictability was required to let the network learn the second task by eavesdropping. So finally, we asked, so having observed that stimulus correlations were required to induce learning, are they also required to maintain a solution after learning? So to test this, we changed the stimulus correlation or predictability from chance level up to strongly correlated, and then gradually back down to chance level again. And what we observed is that networks wouldn't learn the matching task as long as stimuli were uncorrelated. But as soon as stimuli were correlated, networks would learn the matching task. And as we removed the correlation, they would maintain the solution. And we think this could be very important for coming back to neuroscience. This could be very important because this means that transiently introducing stimulus correlations can create stimulus representations through predictive learning that can then benefit working memory tasks. So in other words, if an animal or some form of agent is stuck in a difficult task, then changing the correlation structure of the environment could catalyze learning before bringing the environment back to normal again. So with that, I would like to thank you very much for your attention, and I'd like to thank my supervisors, Sanjay and Tim. And I'm happy to take any questions that you have, and also later by email. Thank you.
Okay, any questions? Okay, if there are no questions, well, given that we are running a bit late, so let's thank the speaker. And this concludes the oral sessions. So yeah. We're going to take a short